At the end of the chapter on pressure, there are 14 problems for you to do. We've already worked through about half of them in the course of the lectures. It leaves us to do problems 9 through 14. And problem number 14, which is on page 87, I'm not going to do that one at this time. In the unit on flow, later on in the course, we'll discuss bifluid manometers later. So omitting number 14, we have problems 9 through 13 to do. And rather than my writing out the complete solutions, I think what I'll do is kind of talk to you about it and lay out the solution, and then you go ahead and try it yourself, and then check your answers against the solutions I have posted. So I have a detailed solution document showing every step in the calculations. So problem number 9 says that water flows through a pipe in the diagram as shown below. So here's water flowing through the pipe. Determine the height h, which is here, if the gauge pressure at A is 35 kilopascals. And here's the point A. Might seem kind of odd when you first look at it. How would we determine the pressure at point A? Well, this is a manometer below the pipe, and manometers do measure pressure. But the easiest way to think of these often is to try and find some equation that you can write that includes the term you're trying to solve for. So is there some kind of equation, equality that we could write that includes the term, the pressure at A? One thing that you can rarely go wrong with is that pressure is equal, has horizontal levels in the same fluid. So would you agree with me that the pressure at this point is equal to the pressure at this point, because those are a horizontal level in the same fluid? So we can write an equation to say the pressure at this point on the left is equal to the pressure at this point on the right. And that equation, as long as it includes the term we're trying to solve for, which in our case is h, should lead us to the solution. So what is the pressure at this point? Right here I'm circling. What is the pressure at that point? Well, it's everything pushing down above it. So what is that? Well, it's the total pressure, absolute pressure at A, whatever is there is pushing down, plus 60 centimeters of water, plus h centimeters of water. That's the total pressure at this point, which is getting kind of messy here. And that's equal to the pressure on the right-hand side right here. What is the pressure at that point? Well, it's equal to h centimeters of mercury plus atmospheric pressure. Now notice that we're given the gauge pressure at A, not just the absolute pressure. So I'm going to break this apart and call it atmospheric plus the gauge pressure at A, right? Because atmospheric plus gauge is absolute. Now I'm going to have 60 centimeters of water plus h centimeters of water plus h centimeters of mercury. Well, you can't combine heights of different fluids. They have to be the same fluid. So if we converted all of our heights of water to heights of mercury, then we could combine these terms. So how do we do that? How do we convert a height of water to a height of mercury? Just look up here for a sec. If I took 60 centimeters of water and wanted to know how many centimeters of mercury that was equivalent to, you can multiply by the ratio of specific gravities. The specific gravity of water is 1, and the specific gravity of mercury is 13.6. And I'm putting the small number over the big number because I know, and you know, that it would take a lot smaller height of mercury to exert the same pressure as 60 centimeters of water. And you say, well, Barry, the units don't cancel. They don't look right, do they? Well, no, they don't cancel because this is an inverse relationship. Right? Inverse relationships, you can't follow units. You have to use logical statements or memorize formulas. And I'm not going to try and even think up a formula for this. It just makes sense that it's going to take less mercury to exert the same pressure as a large column of water, so divide by 13.6. So in my expressions down here, rather than multiplying by this ratio every time, I could just say multiplying by 1 over 13.6 is the same as dividing by 13.6, right? So I can write this as 60 divided by 13.6, and that is now centimeters of mercury instead of water, plus this term H would be H divided by 13.6 is now centimeters of mercury. And that's equal to, on the right hand side, I already have H centimeters of mercury, and I have P atmospheric. Now, as promised here, I can cancel P atmospheric, so that makes it simpler. Now, you'll want to convert 35 kilopascals to centimeters of mercury. So that can be done. For example, 35 kilopascals, and convert that to centimeters of mercury. Atmospheric pressure is 76 centimeters of mercury. Divided by 1 atmosphere in kilopascals is 101.325 kilopascals. Yes, of course, I'll give you all these conversions on a test. And this term here works out to be 26.25 centimeters of mercury. That's the gauge pressure at A. This 60 over 13.6 turns out to be 4.41 centimeters of mercury. So you have those numbers on the left-hand side. You can bring this over. H over 13.6 is the same as 0.0735 times H centimeters of mercury. Bring that to the other side, subtract it from 1H, and you'll wind up with 0.9265 H centimeters of mercury is equal to whatever number is over here, and then dividing by 0.9265, you'll find the value of H. So you go ahead and finish that up and compare it to the solutions that are posted on Blackboard. Problem number 10 says find the gauge pressures in inches of mercury at points A and B and C in this pipe filled with flowing water as shown. So here's the water flowing from right to left, goes through a constriction where the pressure will drop, and when it widens out, the pressure increases. So this is actually an intro to our next chapter on flow, where we'll study this kind of system, but it's a good intro to get us started. You can see by looking at this, we have a manometer here that's open to atmosphere. I admit the problem probably looks pretty daunting, but it's actually very simple once we think about it a bit. Let's say we want to find the pressure at A, right here. How can we do that? Well, I would suggest you write an equation that includes the term pressure at A. Well, what equation could we write? Well, you can't go wrong if you can find a place, a horizontal level where the pressures are equal. And can I not say that the pressure at this point in mercury is the same as the pressure here and here and here? Sure you can. They're all horizontal levels in the same fluid. Since we're starting with A, we'll just deal with A, and we have the manometer on the right hand side. That's all we need. We'll only have one unknown. Here's what that would look like. Okay, so the total pressure at A, I'll write this down here if I can. P absolute at A plus, I'm going to add up the pressures to this point, this red line. What are they? It's the total pressure at A plus 8 inches of water plus 7 inches of mercury, right? But I want them all in the same type of fluid. So 8 inches of water If I divide that by 13.6, I'll have the equivalent number of inches of mercury, right? So 8 inches of water divided by 13.6 gives me the equivalent height of mercury, plus 7 inches of mercury. That would be the pressure right here at this point. And that is equal to the pressure way over here, which is equal to what? 5 inches of mercury plus P atmospheric. That's 5 inches of mercury plus P atmospheric. Now notice we are asked to calculate the gauge pressure. So it would make it easier for me if I broke this absolute pressure apart and just called it P atmospheric plus P gauge at A, and so on. And then you see I can cancel atmospheric pressure from both sides and sum up your inches of mercury, and you'll have it. Just collect all your numbers to the right hand side, and if you want to convert it to a different unit when you have inches of mercury, just do so. So what we're asking for here, it just says inches of mercury, so that would be too easy. On a test I'll have you convert it to some other unit, but you can simply add those up. So that looks pretty scary, I admit, but when you break it down, really it's a very simple solution. Find a horizontal level in the same fluid, and then you can say pressures are equal, and you have an equation and just include the terms that you want to solve for it. You can write a similar equation. You can say the pressure at B plus 6 inches of water plus 9 inches of mercury is equal to 5 inches of mercury plus P atmospheric. To solve for C, you'll say the pressure at C plus 12 inches of water plus 3 inches of mercury is equal to 5 inches of mercury plus P atmospheric. Easier than you thought, isn't it? Check the solutions in the document that's posted and make sure you work through this. Don't just look at them and say, I know how to. Make sure you go through the process. Question number 11. This looks interesting. It's a manometer connected to a water line. Here's the water line. And determine the gauge pressure in PSI this time in the line at point A. So where's that? Well, that's right down here. That's point A. We got to calculate the pressure at point A. Now, if we could write an equation that included the term A, or pressure at A, we should be able to solve it. What kind of equation could we write here? Well, how about everything pushing down on point A is the total pressure at A, right? Can we do that? I'm just going to say the total pressure at A. I'll call that P, absolute pressure at A. And you know what? I'm going to break it apart right now into atmospheric pressure plus the gauge pressure at A, because we're asked to solve for the gauge pressure. Notice, I also see we have an atmospheric pressure term in here that's going to cancel out and make it easier for us. So what I'm saying is the total pressure right here at A is atmospheric plus gauge. What's it equal to? It's equal to everything pushing down on top of it. What's pushing down? Well, I can see 30 inches of water is pushing down. Right? Now what about above that? Well, I have no dimensions up here, but it's a kind of a loop, right? So whatever is pushing down to the right will be offset by what's pushing to the left. Well, that's kind of hokey maybe, but think of it this way. This should work. Here's a horizontal level in the same fluid, right? We got water and water at the same level. So whatever the pressure is at this point, it's also equal to the pressure at this point. Now keep going. The horizontal level in the same fluid, I can say pressure is equal here, because now we got mercury at the same level. So it doesn't really matter what the pressure is in this loop, but because I can say the pressure at this point equals the pressure at that point equals the pressure at that point, I can add up what's above it. What's above this point? Well, I can see there are 15 inches of mercury, plus on top of that we have atmospheric pressure. So I think you can see it now, right? Absolute pressure, atmospheric pressure will cancel. We'll solve for gauge pressure at A. You simply need to convert this to the same unit, the same fluid. This we want to convert this to inches of mercury. By dividing by 13.6, add the two together, you'll find the gauge pressure at A, and you can convert that to psi. Not so bad as it looks, eh? Right, finally we have problems 12 and 13. I'd like to do 13 first because it's quite simple, and then we'll save 12 for the end. So problem 13, the pressure at the liquid surface in a tank, which is like right here, is 4 psi larger than atmospheric pressure. Determine the height, h, this would be this here, if the liquid in the tank is water or mercury. So let's think about it for a second. If atmospheric pressure was the same as the pressure in the tank, then the level of mercury would be the same, or the level of water, whatever's in the manometer, it'd be the same height because it's the same pressure, but you can see the pressure in the tank must be greater than atmospheric because the pressure in the tank is pushing the liquid up against atmosphere. And the difference in height is equivalent to 4 psi. The bigger this difference in pressure is, the larger is the height. When there's no difference in pressure, there's zero height. So this is the difference in pressure, h. And we're asked to calculate that, or convert it really, to feet of water. That's just a simple conversion problem. If you said 4.0 psi, and we're asked what is that as a height of water, just use atmospheric pressure as a conversion factor. We know that 33.9 feet of water is 1 atmosphere, and there's 14.70 psi is 1 atmosphere, and that'll give you the feet of water that is equivalent to h. That is, h is that amount. If it was centimeters of mercury, it would be the same process, but you would this time multiply by atmospheric pressure in centimeters of mercury, which is 76 centimeters of mercury, and divide by 14.7 psi, and you would get centimeters of mercury, and that would be equal to the height h in the manometer. If it was mercury, it would be a small amount. If it was water, it would be a lot more, because mercury is 13.6 times denser than water. That's it for problem number 13. So the last one here is problem number 12. It's kind of interesting. It says a mercury manometer is connected to the inlet and outlet of a water pump. So here's that manometer. The left leg is connected to the inlet. The right leg is connected to the outlet. Now the symbol for a pump is the letter P inside a circle, and you can pretty obviously see where the inlet and outlet are, because pumps are designed to increase pressure. So the high pressure side is at the outlet of the pump, pushing the mercury down, and the low pressure side is the inlet, where the mercury is lifted up. We're asked to determine the pressure increase created by the pump. In other words, what's delta P? Delta P, the pressure difference, wouldn't that be P out minus P in? That'd be the pressure difference, right? So how are we going to do that? Can we write an equation that includes the terms P out and P in? Then we can collect them. P out minus P in is delta P. Can we not say that? I'm going to say the difference in pressure, delta P, will be P out minus P in. If we can write an equation that includes the term P out and P in, we'll then group these together and rearrange the equation and solve for delta P. What would that equation look like? What would it be? Remember that horizontal levels in the same fluid are equal pressure, and that gives us an equation. And I can see right here is a good spot to say that's true, because these are horizontal levels in the same fluid. Those pressures are equal. And what's the pressure on the left? And that'll be equal to what's the pressure on the right. And you can see we have the terms P in and P out in it already. Let's go down the right hand side. It looks like it'll group easier that way. I'll say P out plus this height of water. What height is that? Well, it's H3. What are the units? We're not told We're just not told, so we'll just make one up. H3 centimeters of water plus H2 centimeters of water. Is that not the pressure at this point right here? Sure it is. That's the total pressure at that point. It's the pressure at the outlet plus H3 centimeters of water plus H2 centimeters of water. And that pressure is equal to the pressure right over here. What is that pressure equal to? Well, that would be equal to P in, right up at the top, plus H3, we'll call it centimeters of water, plus H2, but this is centimeters now of mercury. I think I have all the terms. So that's it. Notice that we have H3 centimeters of water on both sides. We can cancel that. That's looking a little bit better. So we'll have delta P will be equal to, on the right hand side I've got H2 centimeters of mercury, and then we'll bring H2 centimeters of water to the right. That'll be minus H2, but why not convert that to centimeters of mercury by dividing by 13.6 centimeters? And now it's centimeters of mercury. Delta P H2 minus this term here becomes 0.0735 H2, that's centimeters of mercury, and then subtract 0.0735 from 1, H2 becomes 0.9265 times H2 centimeters of mercury, and then, well, that's it. If we knew a dimension for H2, we could multiply it by our 0.9265 here, but we're not given that. Nor do we know if it's centimeters. It could be inches or some other unit, but that's all we can calculate, and that would be the difference in pressure produced by this pump. Now that's it for the problems in this chapter. I would again encourage you to work through them using the printed solutions that are posted on Blackboard as a guide.